Dear students, this is our 30th lecture on organic reaction mechanism, and today we will start with a new chapter, that is nucleophilic aromatic substitution. Nucleophilic aromatic substitution can take place by different types of mechanisms, and in this lecture we will concentrate mainly on SNAr mechanism, that is nucleophilic substitution. AR is for aryl. So basically a nucleophilic aromatic substitution is a substitution reaction where a nucleophile displaces a good leaving group. So only difference from aliphatic nucleophilic substitution is that here the substrate involved is having an aromatic ring, whereas in aliphatic nucleophilic substitution the substrate involved was aliphatic in nature. Rest of the things they remain same. The attacking species is a nucleophile and there must be some good leaving group, and in most of the nucleophilic aromatic substitution reactions the leaving group is a halogen. Based on the type of reactions and or the mechanism which these nucleophilic aromatic substitution reaction follow, they can be broadly classified into 4 types. First is SNAr mechanism. So this type of mechanism is involved in aromatic halides where the reaction is activated due to the presence of lactone withdrawing groups either at ortho position or at para position to the leaving group, and as I have told you that leaving group in most of the cases is a halide ion. So these types of reactions where the aromatic halides they are activated by a lactone withdrawing group presence at ortho or para position, they are called as SNAr mechanism is followed in such type of nucleophilic aromatic substitution reaction. Then there are other types of nucleophilic aromatic substitution reaction which follow benzene mechanism, and these types of reactions they are catalyzed by very strong bases, and they proceed through aryne intermediates. Aryne means benzene as the intermediate during the reaction, and most commonly used strong bases in these types of reactions, they are potassium amide or sodium amide. Then third type of reactions are those reactions in case of nucleophilic aromatic substitution where the reaction is initiated by lactone donors. So such type of reactions they follow SRN1 mechanism. So a free radical type of mechanism is followed in such type of reactions, that is substitution radical nucleophilic unimolecular. So these types of mechanism is followed where the reaction is initiated by lactone donors, and in some nucleophilic aromatic substitution reactions even SN1 type of mechanism is also followed, and SN1 type of mechanism is followed mainly in reactions where nitrogen of a diazonium salt which is having a positive charge is replaced by a nucleophile. So basically overall if we say the reaction is such type of aryl compounds where X is some halogen and Y is generally an electron withdrawing group, when they are reacted with some nucleophile, then X is substituted by the nucleophile, and these types of reactions they are called as nucleophilic aromatic substitution, and these types of conversions may follow any of this type of mechanism. And in the present lecture we will concentrate mainly on SNAr mechanism, that is aryl nucleophilic substitution. Now this SNAr mechanism is also known as addition elimination mechanism, and many types of reactions they are taking place by this mechanism, and this is a bimolecular mechanism. Here the reaction is completed in two steps. In the first step, the aryl halide reacts with a nucleophile, which is a slow process, and this type of an intermediate complex is formed during the reaction, where the nucleophile also get attached to the carbon where the halogen is attached. So in the first step we can say the nucleophile attacks the ipsocarbon. Ipsocarbon is the carbon to which this nucleophile will get attached where the leaving group is present. So carbon having the leaving group is ipsocarbon, and nucleophile will get attached to the ipsocarbon of the aromatic ring. And this is a slow process, and we know that the slow step is the rate determining step. So because here the aryl halide as well as nucleophile both are involved in the formation of this complex, that means rate of reaction will be dependent on the concentration of aryl halide as well as nucleophile. So that is why this reaction is a bimolecular reaction, or we say that mechanism is a bimolecular mechanism. And in the second step, the leaving group is eliminated and aromatic ring is regenerated, and this type of mechanism is generally found where activating groups they are present on this ring, and this is the most common mechanism which is present in aromatic nucleophilic substitution reactions. Then evidence for existence of this type of bimolecular mechanism comes from, say, if we are having this type of substrate 2,4,6-trinitroanisole. So all these three groups, they are electron withdrawing groups, and when these electron withdrawing groups are present at these positions, that means this carbon will become very electrophilic, so that it will be easier for the nucleophile to attack this carbon, this ipsocarbon. And when we are using ethoxide as the base, then this type of salt is formed during the reaction, and these salts have actually been isolated and their structures have been established by NMR and X-ray crystallography. Similarly, if we start with 2,4,6-trinitrophenitol, you can see over here the difference between this substrate and this substrate only is that here we are having methoxy and here we are having ethoxy. So when we react this ethoxy substrate with methoxide base, then also same product will be formed. If we start with methoxy substrate and react with ethoxy base, then also we will get the same product, same type of salt will be formed. So when these two reactions they were performed, we got the same product whose structure was also established by NMR and X-ray crystallography. So formation of these types of salts, which are called as Meisenheimer salts or Meisenheimer-Jackson salts, is an evidence for existence of the attack of the nucleophile on the ipsocarbon of the substrate to form these types of substrates. So the isolation of these types of intermediate tells us that the reaction is taking place in those two steps, and the next step here is not followed because both they have the equal energy. Then there is another spectral evidence for the existence of two types of intermediates in the first step. Either a pi complex is formed, or that pi complex then is transformed into another radical ion radical pair intermediate, which ultimately leads to the formation of the intermediate complex which is formed in the first step. So this has also been studied through spectroscopy, that when picryl chloride is reacted with hydroxide ion, then first this hydroxide ion will interact with the aromatic ring and this type of pi complex will be formed, and then this pi complex will change into a radical ion radical pair type of intermediate, which will ultimately be transformed into the intermediate involved in the first step of SNAr mechanism. Then another evidence is obtained from the studies of effect of leaving group on the reaction mechanism. So for example, if we are having this type of substrate which is substituted by nitro groups at the ortho and para positions, then we change this X from say chlorine, bromine, iodine, SOPH or SO2PH or para-nitrophenoxy, and then we determine the rate of reaction for these SNAr reactions. Now if the mechanism of SNAr was similar to SN1 or SN2 mechanism in case of aliphatic nucleophilic substitution, that means in those cases AR-X bond would be broken and it should be the rate determining step. And we know from the mechanism of SNAr that the breaking of this bond is not the rate determining step. Rate determining step is when the nucleophile gets attached to the aromatic ring at the ipsocarbon to give us a intermediate complex. So that means in case of aromatic nucleophilic substitution, breaking of this bond is not the rate determining step. This is a fast step, which is the second step. So if SNAr mechanism is operating, that means a change in the leaving group should not have much effect on the reaction rate. So this is what is seen when this experiment is done, then that when this dinitro substituted halogen derivative was reacted with piperidine base, and by changing the X to these groups, it was found the rate of the reaction differed by only by factor of 5.12. So that means if this breaking of this bond is the rate determining step, then the rate would have different depending upon the strength of these groups, because iodine carbon iodine bond, carbon chlorine bond, carbon bromine bond, carbon sulfur bond, they have different strengths. So rate will be much more different than actually which is obtained in this case. The rate is differed only by 5.12 times, a factor of 5.12. So which means that the mechanism followed is not SN1 or SN2, and here the rate determining step is not the breaking of this bond. So this is another indirect evidence that the mechanism followed in aromatic nucleophilic substitution is different from aliphatic nucleophilic substitution. Then another evidence is that nature of this group, leaving group, affects the rate at which the nucleophile attacks. So an increase in electron activity of this leaving group causes a decrease in the electron density at the site of attack. If this is more electron active in nature, that means this will attract electron density towards itself in a better way, and because of that a faster attack of nucleophile will be possible in this case. So when electron activity of X is higher, that means this carbon is more electrophilic and nucleophile will attack with more easily as compared to the group where the electron activity is less in this case. So this experiment was done that it was found if X is fluorine or if X is iodine, it was found that with iodine which is less electron active than fluorine, the rate of reaction was, if rate of reaction was found to be 1, that the rate of reaction was found to be 300 times faster when X is fluorine. So this tells us that increase in electrode density at the leaving group will also affect the rate of reaction in case of aromatic nucleophilic substitution. So this is a good evidence which tells us that mechanism is different from SN1 or SN2 type of mechanism, and in case of SN1 and SN2 type of reactions, the fluoro is the poorest leaving group amongst the halogen, and iodine is most suitable as a leaving group in case of SN1 and SN2 type of reaction. So this is how we can differentiate between aromatic nucleophilic substitution and aliphatic nucleophilic substitution based on the electron activity of the leaving groups in case of nucleophilic substitution, in case of aromatic and aliphatic, and this is known as element effect, because the same fluoro group in case of aliphatic nucleophilic substitution is the poorest leaving group, and here the rate of reaction is 3300 times more as compared to iodine as a leaving group. So on the basis of this evidence also we can tell that the mechanism followed in aromatic systems, aromatic halogen compounds, is different from aliphatic halogen compounds which follows SN1 and SN2 type of mechanism. Then another evidence which comes is the effect of base catalysis with amine nucleophiles on SNAr types of reactions. So these reactions where the nucleophile is a secondary amine, the first step is that in the presence of these base, these types of ionic species they are formed, and their reaction elimination of proton is from here from the secondary amine is catalyzed by addition of another base which will enhance the rate of the reaction. So bases could not catalyze the step 1 of these types of reactions when amines they act as nucleophiles, but these bases they can catalyze step 2 of this aromatic nucleophilic substitution. So this evidence also indirectly tells us that SNAr mechanism takes place in 2 steps, not in 1 step. So this is another indirect evidence which tells us that the SNAr mechanism is different from SN1 or SN2 type of mechanism. So this lecture has been taken from organic reaction mechanism by Jerry March, and some additional sources from the internet have been used. Thank you very much.